All right, so we're going to learn about null spaces and column spaces of a matrix and how they relate to a matrix transformation. Here's a handy summary to help with some of the terminology of this section. You'll notice that the picture on the screen is a little different from the picture in your notes. What is different? Yes, I rewrote the way you calculate. That was just an alternate notation that means the same thing, right? So you could add that. It's t of x equals ax instead of writing x goes to ax, right? What else is different? 0 is in the range, right? Because the range is not necessarily all of the codomain. So the light blue cloud represents the codomain. The darker blue cloud represents the range. And 0 is always in the range. You always can get 0 via a matrix transformation. Okay, so 0 is supposed to live in the range. Okay, so just to walk through this picture, if you've got a matrix transformation, t of x equals a times x, your domain is your set of all your inputs. So that's the light blue cloud is the domain. The null of a is a subset, also a subspace, always. We can prove it, but I'll just giving you the punchline. The null of a is a subspace of the domain, and we define it as the set of all things from the domain that go to 0. Right? It's a set of all things that you plug into T and multiply a by that gives 0 as an output. That give the 0 vector as an output. And then, so that's the definition of the null space of A, and we abbreviate it null A. The definition of the column space of A, which we abbreviate col A, is the range of your domain. It's a set of all outputs A times X. You could also think of it as the set of all linear combinations of A. That's why it's called the column space. It's the set of all linear combinations of A. All right, so we'll do some examples. Hopefully we'll make that clear. So here I've got a matrix A, and I want to know, is this vector x, 1, 4, 2, 5, in the null space? So the definition of the null space is the set of all things from the domain that when you multiply a by them, you get 0. So I want to know, is a times x equal to 0? Right? If a times x is 0, then x is in the null space. It's just the definition of the null space. It's a set of all things that you multiply a by to make 0. So quick check, 0, 1, negative 1, 1, 2, 0, 0, negative 1. Multiply that by 1, 4, 2, 5. Make sure we're allowed to do this. This is 2 by 4. This is 4 by 1. Yes, the inner dimensions match. My output should be a 2 by 1. So I do row times column. So I have 0 times 1 plus negative 1 times 4 plus 2 times 2 plus 0 times 5. And then next row times column, I have 1 times 1 plus 1 times 4 plus 0 times 2 plus negative 1 times 5. And I get 0, 0. So ax does equal 0, which means that x is in the null space. Okay, we can call it the null space of A or null A for short. So null is like a word for 0, right? So it's the set of all things that go to 0. Null space. All right, is 1, 4, 2, 5 in the column space? So same vector. It does live in the null space. Does it live in the column space? So remember, the definition of the column space of a matrix is the set of all linear combinations of its columns. So if you took a linear combination of these columns of A, 0, 1, negative 1, 1, 2, 0, 0, negative 1, throw some scalars on there, add them together, could you ever possibly get 1, 4, 2, 5? No, because what do you get when you take, where do they live? Linear combinations of the columns of A live in R2, right? So this is impossible. No linear combinations of the columns of A live in R2, right? So that's just, I don't even have to check, right? There's nothing to do to check. If I had given you a vector in R2, I would have to do some work to figure it out, right? But it's not even possible. So now I'm giving you a vector 3, 7. Does it live in the null space? Well, I would have to, that means is A times that vector equal to 0? So my A, can't remember, 0, 1, negative 1, 1, 2, 0, 0, negative 1, times 3, 7. Does that equal 0? Well, first, check. This is 2 by 4. This is 2 by 1. Am I allowed to multiply those together? No. So this is definitely no, right? Can't even multiply them, so I don't have to, I'm not even going to do the multiplication to check because it's impossible. Is 3, 7 in the column space of A? This might be possible, right? Because if I take a linear combination of the columns of A, throw some weights on those columns, can I get 3, 7? Yeah, 3, 7 lives in the right world, right? It lives in R2, so I might be able to get it. So how would I figure it out? Like, if there are weights that I can put on these columns to build 3, 7. Yeah, just do an augmented matrix. 0, 1, negative 1, 1, 2, 0, 0, negative 1. Augment with 3, 7, and we'll solve. If this is consistent, then yeah, there are some weights that we can put on those columns and build 3, 7. So let's see, this row reduces to 1, 0, 0, 1, 2, negative 2, negative 1, 0, 10, negative 3. So this is consistent. Therefore, yes. There are some weights we can put on the columns of A to build 3, 7, which means that 3, 7 is in the column space. It can be built as a linear combination of the columns of A. Make sense? Okay. All right, here's a 4 by 4 matrix A. I want to find an explicit description for the null of A, right? So that is, rather than giving you a specific vector X and saying, is this in the null space? I want you to tell me every vector that's in the null space. I want you to find all the vectors that get A times them equals 0. Right, so I'm looking for all the vectors X such that AX equals 0. So we just take A, augment with 0, 0, 0, 0. And when we solve it, we get 1, 0, 0, 0, 0, 1, 0, 0, 0, 4, 0, 0, 0, 0, 1, 0. All right, so if I translate this augmented matrix back to equations, this says x1 is 0, x2 plus 4x3 is 0, and x4 is 0. And what's free? Which of my variable? X3 is the free variable. That's the only column without a pivot in it. So x3 is free. So this describes my solutions, but I'm gonna they asked me to write it in a very specific way. We want to give a set of vectors that spans the null space. So I'm going to write this in parametric vector form, and then translate that to a sentence using the word span. I'm going to jump up here. Okay, so parametric vector form means writing my solutions, x1 through x4. My free variable is x3, so that's going to be my parameter, x3. And then x1 is always 0. x2 equals -4x3, right? Because you have to solve for the basic in terms of the free. x4 is always 0, and x3 is free, so you just put a 1 there. So that's parametric vector form of the solution. Those are all the vectors that A times it equals 0. But they asked me to use a word span, the word span here. So this is the span of this vector, 0, -4, 1, 0. Because the definition of the word span is just all linear combinations, which in the case of a single vector just means throw a constant on there, which that's the role that x3 is playing, just a constant. So that's going to be the answer. So it's just the set of all vectors that A times it equals 0. Any multiple of 0, -4, 1, 0. So this is not anything new, right? We've been solving equations AX equals 0 for a long time and writing the solutions. All right, so give any non-zero vector in the null space of A. So any vector in the span of 0, -4, 1, 0. So just, I don't know, 0, -8, 2, 0. I just multiplied everything by 2. So I made x3 a 2. All right, so moving on from the null space, I want to find an explicit description of the column space by giving a set of vectors that span the column space of A. All right, so this one is like way easier than the null space one, because the definition of column space is the set of all linear combinations of the columns of A, right? And the definition of the word span is the set of all linear combinations of the things in the brackets. So my column space of A is the set of all linear combinations of the columns of A, so it's just the span of the columns of A. So A, its columns are 1, 0, 5, 0, 0, 1, 0, -2, 0, 4, 0, -8, and 0, 3, 1, -6. It's just the definition of the column space. It's the set of all linear combinations of the columns of A, or the span of the columns of A. It might be that you don't need every single vector in here to build the column space, but we'll talk about that in the next lesson. So give any non-zero vector in the column space, any linear combination of the columns of A will work. So anything in any actual column of A will work, because you would put a 1 as your weight on 1, 0, 5, 0, a 0 on everything else, and add them together. What else would be in here? 0, -4. Yes, thank you. Just copied it wrong. Zero, -1, 0, 2. Where'd that come from? Second column multiplied by -1. Great. And I could add any two together. Like as if I add the first two together, I would get 1, 1, 5, -2. That's 3. I only asked for 1. All right, so that's it. That's the definition of the null space, set of all things that go to 0, the definition of the column space, all the linear combinations of the columns of A. If you know those two definitions, everything else is just like pulling from things you already know. So that's it for the lecture.